Okay. Here we go. So Taylor and Maclaurin series. This is kind of the peak of chapter 11 here. This is kind of the ultimate point you're building to. So I'm going to kind of start out kind of demonstrate to you how they where the kind of logic comes from to build all of this and get the numbers. So first of all, I'm going to take some function and I'm going to write it as a power series. And I'm going to kind of expand it out. So I'm going to have CO plus C1 times x minus a plus C2 times x minus a squared plus C3 times x minus a cubed. Okay. Good. Now, again, just like what we've discussed already, if I have, as long as that x minus a term is less than r, then we can say this is true, right? It's within that range of convergence, it converges, so I can represent this function, whatever it is, as some sort of power series. Okay. So, what we want to do here is sometimes I may not be able to take a function easily and convert it into that building block. Okay, so we want to find another method to do this. Okay, and the way we're going to set this up is I'm going to find maybe a way to determine what each of these coefficients are in terms of the function itself. So say if I know the function, then I can just use some sort of method, some sort of pattern to be able to set up a series if I just know the function. Okay, so to start us off, I want to see what C0 is supposed to be. C0. So if I want to find what C0 is, I need everything, all the C1, C2, C3, all that to go away. Is there a number that I can plug in into this function so that C1, C2, C3, all that would go away? What do we think? Right, we have x minus a squared, x minus a cubed, x minus a to the fourth. Okay. Just plug in a, right? So if I let x equal a, then I'm going to get f of a equals C0 simply. So if we know that this, the function can be represented by a power series, then that CO term is simply whatever f evaluated at that center a is. Make sense so far? I just plugged in a, and we just got CO. Okay. Next thing. I can't really plug in a value very easily to see what C1 is yet. Let's take the derivative of this function now. So if I take the derivative of this function, so CO is going to become 0. I'm just going to get C1 plus, now we do shift over, but also there's going to be a number that comes down each time, right? We're going to get 2 times C2 x minus a plus 3 C3 times x minus a squared plus ... Okay. Now, can I use this to get C1 by itself? Yes, we can. What number do I plug in? A. So I get f prime of a equals C1. So C1 equals f prime of a. Interesting. Okay. We're starting to see something happening. Okay, but we must continue. Right? So let's continue. Let's do another derivative. What's the derivative of C1? 0. What's the derivative of 2C2 x minus a? I think I heard someone say it. 2C2. And then we're going to get plus 3. So plus, bring down the 2 here. So we get plus 6 C3 times x minus a squared. Looks like maybe I'll add on another term. Here we would have had plus 4 C4 times x minus a to the third power. So then we would get 4 times 3. So we get 12 C4 times x minus a squared. Okay, now what's gonna happen if I plug in x equals a? Yeah, so we get 2c2 equals f double prime of a. So what is c2? F double prime of a, not just f prime of a. Okay. Now we have f prime of a, we have f double prime of a over 2. You still may not see it quite yet, so I'm going to take one last step. Okay, and then it should kind of fall together. Okay, we kind of see a pattern happening. Let's do one more. So I'm going to take f triple prime of a, and that's going to be the 2c2 goes away now, and we're going to get 6 times. Oh, this should be the first time. I thought so. First, second. Okay, so we're going to get 6c3. Right? Does that make sense? We should get 6c3. Okay, times x minus a, the derivative of this is 0. Here we're going to get 12 times 2, which is 24, c4 times x minus a, and then plus dot dot dot. Okay? So, or sorry, this should be x still. But then when I plug in x equals a, we get f triple prime of a equals 6c3, or we get c3 equals f triple prime of a over 6. Okay, if you continued on, you're going to get f4 prime of a over 24. You're going to get f5 prime of a over 120. It's going to continue, right? Let's think about what this pattern is. So each time we just have the derivative, right? We just go one derivative down each time, right? Now this is f of a over 1. This is f prime of a over 1, f double prime of a over 2, f triple prime of a over 6. 1, 1, 2, 6, and then like I said, the next number would be 24. Anybody know what that is? What that pattern is? 2, 6. Yeah. Times, well, it's not quite right because it's you're thinking the right way though, right? So to go, maybe this one's might be a bit weird, right? But to go from here to here, I multiply by 2, here to here, multiply by 3, here to here by 4, here to here by 5, right? So this is 1 factorial, 2 factorial, 3 factorial, 4 factorial, 5 factorial, 0 factorial. Those are factorials, right? And you can even see that here, right? Notice I get, 3 times 2, right? And then I got 4 times 3 times 2, which gave me 24 up there. If I did another one, I get 24. I get f 4 prime of a over 24, right? They're factorial. So this means that we can concretely say that if f of x can be written as a power series, with that power series being n equals 0 to infinity of Cn times x minus a to the n power, then Cn is going to be, well, the factorial is on the denominator, right? It's dividing each time, right? It's over 1, over 1, over 2, over 6, that'd be over 24. So the n factorial is on bottom, and then what I'm going to write on the top is f, and I'm going to write it like this: f n of x. That little n up there in the parentheses means that's the derivative you take. So when n is 1, it's the first derivative. When n is 2, it's the second derivative. when n is 3, it's the third derivative. Okay? So this power series for this function is what we call its Taylor series. Okay? So, if we want to see what that looks like, kind of expanded out, right? Then that means that f of x is equal to f, it's going to be f of a plus f prime of a over 1, or just f prime of a. Plus f double prime of a over 2 times x minus a squared, and I'll just put that in, make some more room for that. Plus f triple prime of a over 6 times x minus a cubed. Dot, dot, dot. Okay, so that's if I expanded it, that it would look like this, right? That's kind of what the series is going to be. Now, again, we're going a little slow here just because we're going to have more time to already do this, right? So I want us to look at something really intently here for a moment. If I cut this off, not any of these other terms can just stop there. So I have f of x equals f of a plus f prime of a times x minus a. Does it look familiar? What? What? It actually, the limit definition is in there. Yes, that's very true. If I take f of a and subtract it, and then I divide by the x minus a, that would be the limit definition. If I took the limit, then I would get the derivative. However, what I was more looking for in this case is notice that maybe I'll subtract the f of a still. So I'm going to get f of x minus f of a equals f prime of a times x minus a. Let's say f of x equals y. And then this is, so f of a is going to be some y, some initial y value. Then f prime of a is m, derivative, x minus x prime. Right? That's like, whenever we're taking the tangent line and finding the, get the slope of the tangent line and then get the equation of the tangent line, it's built in this, right? It's this first part, right? So the reason that we can do that is really because of Taylor series, right? This tells us that whenever we're really close to A, that just a linear approximation is going to be pretty good, right? It's going to be pretty close, and that's why we use it, okay? And then, of course, you could just keep going. You keep adding terms. Now, we don't do this part very often. We don't, approximate using the tangent parabola, right? Because that's just not, again, we wouldn't have gotten to this point. But we could totally do that, right? I can approximate by just going more and more lines down. We've done this one several times, but now you can keep adding pieces. And if I go towards infinity, then it would be the same thing. Okay? Any questions for me, woman? So this is the formula for Taylor series. Okay, and we'll do one kind of find the Taylor series for a function before we get done today, or before we go. But this is the formula. Okay. Now, what is the difference between a Taylor series and a Maclaurin series? Well, not much. A Maclaurin series is actually just a special case of the Taylor series. A Maclaurin series, and I'll leave this here. Oh, well, no, that's kind of This is the Maclaurin series of a function. Alright? So what did I do to the Taylor series to go from there to here? Just made a 0. Right? That's the simplest form of the power series, right? Just let a be 0. And we call that series Maclaurin series, right? So if you're asked for a Maclaurin series versus the Taylor series, you're doing the same thing. And just for the Taylor series, you're just letting a be 0, right? Which makes the calculation really easy. Okay? So let's see, I want to see okay, so they write series. Okay. So let's find a Taylor series, or we'll just do a Maclaurin series in this case. Maybe tomorrow we can do like a Taylor series, do some more. But let's do it. Okay. So we're going to find the Maclaurin series of e to the x. Okay, so we're going to see if there's a way that I can take e to the x and represent it as a series. And we're going to use this Maclaurin-Taylor series idea. Specifically, in this case, we're going to use Maclaurin series, right? So I'm going to bring out, again, Maclaurin series. So we need to use the n equals 0 to infinity of f n of 0 over n factorial x, right? So my goal is to figure out what each of these constants are in case to build the series, okay? So let's just start out with, right? So whenever n equals 0, what is that? What does that mean? What is f? What is f0? Right? If that indicates the derivative, right? What we're going to get the first derivative, the second derivative, it's just the original function, right? So we want to find these values, right? So I want to look at a few derivatives, right? So let's take some derivatives of x, right? What is f prime of x? Yeah. Oh, nice. Okay, what's that triple prime of x? Okay, what is that triple prime of x? Okay, what's that? Fourth prime of x. Wow, you guys are just getting us out. Like, how are you just doing this? I mean, we just went 4 derivatives and you just nailed it each time. I have no idea. Yeah, so the derivative of f in each case is just right. So now I'm gonna shift this over slightly. Okay, so now we need each of those at 0, right? Sometimes it might be f at a, but now we're just gonna do 0 since we're just wanting the forward series. So what is f evaluated at 0? 1. Okay. What's f prime evaluated at 0? What's f double prime evaluated at 0? 1. Yeah. How do you guys do this? Just get it. You guys are doing great today. What's f triple prime at 0? 1. Yeah. And then the list would go on from here, right? So each of those, the f values are always going to be 1. Okay. The only thing that's going to change in each case is that n factorial, right? So the best way to do these problems, by the way, is not to necessarily just try to fit it directly into the series, but kind of write out some terms, right? So when n is 0, right, I'm going to get just the original function at 0, which we know is 1. So we get 1 over 0 factorial x is 0, right? And then we're going to have plus 1 over 1 factorial x to the 1 plus 1 over 2 factorial x to the second power plus 1 over 3 factorial x to the cube plus 1 over 4 factorial x to the fourth. Okay, again, I'm just plugging in each of the values. So this is f of 0, this is f prime of 0, this is f double prime of 0, this is f double prime of 0. After 4 prime 0, and we'll just go on, right? On each of those numbers. Okay. So now let's kind of treat this like we did when we were playing like a pattern between sequences, pattern between series. Is there a pattern here between each of these terms? What is it?
Oh, I did a formula.
Yeah, so what's the formula going to be in this case? If I just let it be n each time. Like what's the general n term going to be? Good. We have 1 over n factorial in each case, and then just times x to the n power, or sum from n equals 0 to infinity. I'll write it as x to the n over n power. So this is the Maclaurin series for each of the x. So no matter and actually, yeah, we have like a couple of minutes here. So let's see if we can figure out what the radius of convergence of this series is. Right? Because remember, on the problems we've been doing, we've been wanting to say, oh well, it's within the radius of convergence, so this makes sense. Right? So let's see what the radius of convergence is for this guy. Right? How would I find the radius of convergence of the series? What test should I use? Equation. So I'm going to take the limit as n approaches infinity. We're going to have the absolute value of x to the n plus 1 over n plus 1 factorial times n factorial over absolute value of x to the n. Any arguments here? It's just a n plus 1 over a n, and make sure you're taking absolute value. Okay. How can I rewrite n plus 1 factorial? What is it? In this case, it'd be n plus 1 times n factorial. So you're close, just one term off there. So because we have to include the n plus 1 times n factorial, and then this I could also write as the absolute value of x to the n on the absolute value of x. So we're gonna have this cancel out and this cancel out, so I get the limit as it approaches infinity of the absolute value of x over n plus 1. What is the limit of this? Ah. So it always converges, right? What's my radius of convergence in this case? Right, it's 0, so that means for any x it's going to be true. So what's the radius? It's infinity. So not only does this represent e for specific values, but no matter what x is, this is always equal to e to the x. So the e to the x and this thing are equivalent no matter what x is. So this is really nice. Okay, so that's a good start for today. We're going to do some more tomorrow. We're going to do sine and cosine, others. But we'll start off. So, any questions for me? Yes.
Did you hand out? I walked through.
I have not handled the test today. I went over it. I will hand them out tomorrow. I need to enter the grades. I have them graded. I just haven't had time to put the grades in yet. Plus for number 13, I'm going to add. Yes.
For can you, and I know that like it's probably will tell you to use or which one to use, but can you use either of them on like any?
Yep.
Basically.
Yeah, it doesn't matter. Like you don't have to, for any problem, you don't have to choose like, oh, I have to use Taylor for this one and Florence for this one, or I have to use A equals this for this one.
Okay.
In reality, you can use whatever A is like.
Okay, with one thing, for the other for certain things.
Yeah, of course. Like this one is a lot simpler if you just use 0, right? But something like when we do natural log, that's not going to be easier when you use 0, right? Because natural log of 0 doesn't exist. 1 over 0 doesn't exist. You might want to use something new. Right? So there are easier choices.
Okay. So like for the Taylor series, like you use an F, would you pick I don't know,
Yeah, so, the book actually like will tell you like,
Oh,
oh, use A equals this thing, or use A equals this thing. And then like you say, if it says use the floor, you know it's zero, right? But if it says Taylor, it might say use A.
Okay.
Okay?
Yeah, thank you.
Yep, absolutely. Actually, yeah, I do have to leave early this morning. About to go biking. For a little while, so. Yeah, you too, thank you. Yeah, absolutely, shoot me an email, happy to address it. Luckily, shouldn't be going long tomorrow, so.